Hi, this is Barrett Givens, and in this video we're going to talk about the definition of a homeomorphism, and we will do an example. So a homeomorphism is a bijective function f such that both f and f inverse are continuous. First of all, you might notice we're talking about f inverse here, so we have to be sure that we know that f inverse is an actual function in this case. But since a homeomorphism has to be a bijection, then that means that f inverse exists and is truly a function. So it's okay for us to talk about both f and f inverse. Another way to think about it is that a homeomorphism is a function that satisfies four properties. It's one-to-one, it's onto, it's continuous, and its inverse is continuous. Okay, so it's a function that satisfies these four properties. And if you have such a function, if you have a homeomorphism between two spaces x and y, then we'll say that x is homeomorphic to y. And for this class, we will write that as x homeomorphic to y, which looks like an equal sign with sort of a squiggle over it. Okay, different classes might write it in different ways. They might just write an equals. They might write like a congruent symbol. They might just write like just the squiggle part. Okay, but it'll be something that kind of symbolizes some kind of equivalence. All right. So as an example to talk about, let's talk about this example. Let's say that we have two intervals as subspaces of the real line. So one interval is a comma b and the other one is c comma d. And each interval has one included endpoint and one excluded endpoint. So the first interval, a comma b, has the endpoint a is included and b is not. And the second interval, c comma d, c is not included, but d is. To show that these are homeomorphic, the definition of being homeomorphic is that there exists a function, so we have to give an existence proof. We have to find a function, f, that goes from one interval to the other interval. And since these are subsets of the real line, the easiest way to kind of picture, at least for me, to picture functions from the reals to the reals is on a graph. And so I'm looking at a graph where my domain is the interval from A to B with A included, and my codomain is the interval from C to D with D included. So I want a function that sort of lives inside of this rectangle right here. I want a function that's kind of like somehow inside of this rectangle right here. And I want it to be one-to-one and onto, and I want it to be continuous. So like I don't want to do something completely wacky. Like I don't want to do something like this, although that would be a function that goes from AB to CD. It's not going to be the kind of function I want because this function, for example, is not one-to-one. Okay, it's not one-to-one because it fails the horizontal line test, for example, right there. Okay, so I don't want a function like that. I want to kind of keep it simple. Okay, so let me erase this square. All right. I think what I'd like to do to keep it as simple as possible is I just want to make my function be a straight line function, a linear function. And I will have it take, the endpoint of one interval to the endpoint of the other interval, and then just kind of make a straight line to the other endpoints. And because there's sort of a difference in the endpoints here, one endpoint is included and one is not. I'm going to match up the endpoints that are included. So I want my function to go from the point a comma d down to the point b comma c, but I will not include b comma c. And so I'm going to make a straight line that goes like that. Okay. So just looking at the picture, is that a one-to-one function? Yes, you can see that it passes the horizontal line test, or you can think about, if you had um, two inputs that were different, then their outputs would also be different. It's onto because the y coordinates kind of stretch all the way from C up to D, including D. It's continuous. It looks like it's continuous because, the sort of informal way is, well, I've drawn it without lifting up my pencil off the page. And its inverse will also turn out to be continuous. Let's go ahead and find the equation for it so that we can think about this just a little bit more. All right, well, this is a line, and so I can use the formula for a line. Y minus y1 is mx minus x1. And for my x1, y1, I could use the point a comma d, or I could use the point b comma c. I think I'll just use a comma d, just sort of chose it at random. And then for my slope, I have 2 points, so I can use the slope formula. y2 minus y1 all over x2 minus x1. All right, so if I do all that and I simplify a little bit, I think what I get is y is equal to c minus d over b minus a times x minus a plus d. And just to check, I like to just check if I plug in a for x, what do I get? If I plug in a for x, this whole first term becomes 0 and I get d. So when I plug in a for x, I get d, and that shows that it goes through the point a comma d. What if I plug in b for x? If I plug in b for x, the b minus a's cancel, and I get c minus d plus d, I get c. So if I plug in b for x, I get c for y, showing that it goes to the point b comma c. Okay, so I think I did it correctly. All right, so that means that my function is c minus d over b minus a, x minus a plus d. I can find the inverse. I'll write the inverse as f inverse of y by just solving this for x, right? I can just solve this for x. And so I would get b minus a over c minus d, y minus d plus a. And I can look at those two functions. Those both look like, straight line functions. They're formed out of a composition of the identity function, f of x equals x, or f inverse of y equals y, composed with subtracting a constant, then multiplying by a constant, and then adding to a constant. Those are all things that we know are continuous. And so we can see by looking at what these two functions are, that both of these functions are continuous. Furthermore, I think we can say that since f has an inverse, f inverse of y, then that means f has to be 1-to-1 and onto. Both f and f inverse have to be 1-to-1 and onto because they are invertible. All right, so this function f is a homeomorphism that takes the one interval to the other interval, and therefore these two intervals are homeomorphic. Now, what does it mean to be homeomorphic? When you talk about two spaces being homeomorphic, you're saying that all their points can be like paired up, okay? So they have the same number of points. They can be matched up in some nice way. But then furthermore, the open sets can kind of be paired up. So like every open set here corresponds to an open set here. And every closed set on one side corresponds to a closed set on the other side. And so everything about the open and closed sets, the interiors, the closures, the boundaries, everything kind of has to line up because it's like we have a bijection of points and a bijection of open sets. And so it's really a way of saying that the two spaces are topologically the same. Okay. So this says that if you have two intervals that have just one endpoint included and one not included, it doesn't matter how long the intervals are, it doesn't matter where they are along the number line. Just anytime you have two intervals of this type, topologically, they're really kind of the same. So like the interval, if I were to look at the interval from 0 to 1, that's topologically equivalent to the interval from 8 to 2024, which is topologically equivalent to the interval from negative, so let's make it open at -9, closed at 17. Okay? So it's saying that all of these intervals, as long as you have one endpoint included and one not, that these are all topologically equivalent. They've just been kind of like maybe stretched or slid back and forth on the number line, but topologically, they're the same thing. And as it turns out, we don't quite yet have the tools, all of the tools to prove all of this, but as it turns out, all intervals on the real line have one of three types. And so the first one is intervals that are uh, intervals that do not include either of their endpoints. So if I look at intervals that don't include either of their endpoints, those would be intervals of the form a comma b, an open interval, or a comma infinity, or negative infinity comma b, or negative infinity to positive infinity. The second type of interval would be intervals that have one endpoint included and one not included. And so that might look like the two that we just talked about, or an interval that looks like closed at A up to infinity or negative infinity up to closed at B. And then the third type is intervals where they're both included. And so that would just be A comma B closed. We can't have any unbounded intervals of that type because you can never include infinity when you're looking as a subset of the reals. Okay, so it turns out that the intervals in each type, they're all topologically equivalent. And so I can say any interval of the form A comma B is actually homeomorphic to an interval of the form A comma infinity. And the intervals in different areas here are not homeomorphic, although we're going to have to wait until later in this class to learn exactly why they're not homeomorphic. Okay, thank you for listening.